Hello everyone. Welcome to today's session on Euclid's geometry. Let me start with a question. Have you ever wondered how ancient people measured their land after a flood destroyed all the boundaries? Well, that's actually how geometry began. The word geometry comes from two Greek words, geo, meaning earth, and metrein, meaning to measure. So literally, geometry means measuring the earth. Thousands of years ago, civilizations like Egypt, Babylonia, India, and Greece faced practical problems. The Egyptians, for example, had to redraw land boundaries every time the river Nile overflowed. They used clever rules for calculating areas and even the volume of a truncated pyramid. Imagine cutting off the top of a pyramid and finding its volume. Pretty smart, isn't it? So, in its early days, geometry was not about theorems or logic, it was about solving real problems in daily life. Now let's move to India, where geometry was equally fascinating. Excavations at Harappa and Mohenjo-daro, yes, the Indus Valley civilization, show cities with neatly planned parallel roads and underground drainage systems. They even had standard-sized bricks with the ratio of length to breadth to thickness as 4:2:1. Later, during the Vedic period, the Salva Sutras gave detailed instructions for constructing altars. Some were square, some circular, and others combined shapes like rectangles, triangles, and trapeziums. And then comes the beautiful Shriyantra from the Atharvaveda, 9 interwoven isosceles triangles that together form 43 smaller triangles. These were precise geometric constructions, but here's the catch. The focus was on accuracy of building, not on explaining why they worked. So in India, geometry was practical and ritual-based, but already highly advanced. Welcome, everyone. Have you ever wondered how geometry, a subject we now associate with logical reasoning and proofs, evolved into the structured science it is today? Well, the journey wasn't a straightforward one, and it didn't happen overnight. Geometry originally started as a practical tool used by ancient civilizations like the Babylonians and Egyptians, who applied it to solve real-world problems such as land measurement and construction. They didn't focus on proving the rules but rather on applying them to practical tasks like reorganizing land after the Nile flooded or calculating the volumes for granaries. They used geometry to get results, not to understand the reasoning behind them. But everything changed when the Greeks entered the picture. Around 600 BCE, Greek thinkers like Thales and Pythagoras shifted the focus from practical geometry to theoretical geometry. Instead of just using rules, they asked, why do these rules work? They began seeking proofs for geometric concepts, not just results. The Greeks emphasized deductive reasoning, which meant that they wanted to understand the logic behind why something worked and how to prove it, rather than just applying it. This was a huge leap for geometry. It transformed the subject from a practical tool into a logical science built on reasoning and proofs. One of the first Greek mathematicians to make this leap was Thales of Miletus, who is credited with the first known geometric proof. He proved that a diameter of a circle bisects the circle, dividing it into two equal parts. This may sound simple to us now, but back then, it was revolutionary. Thales' work laid the foundation for others to follow. Then came Pythagoras, around 572 BCE, who took things even further. He developed many geometric properties and theories, including the famous Pythagorean theorem, which shows the relationship between the sides of a right triangle. Pythagoras didn't just stop at individual results, he built entire systems of geometric thought that influenced generations of mathematicians to come. But the culmination of this work came with Euclid around 300 BCE. Euclid didn't just write down geometric facts, he created an entire logical framework for geometry. His 13-book work, Elements, became the cornerstone of geometry as we know it. Euclid took the discoveries of earlier mathematicians and arranged them into a logical structure, proving each concept step by step. His work showed how geometric facts could be deduced from simple, clear axioms and postulates. So, the big takeaway here is that the Greeks made a fundamental shift in geometry. They moved it from a practical, rule-based system used by civilizations like the Egyptians and Babylonians to a proof-based science. Thanks to the work of Thales, Pythagoras, and Euclid, geometry became a subject based on reason, logic, and proof, a far cry from its origins in practical land measurement. And that's the foundation of how geometry transitioned from being a practical tool to a science based on proofs and logical reasoning. In the next video, we'll dive into Euclid's postulates and axioms, which were the building blocks of all geometry. See you there. Let's dive into Euclid's approach. He began with basic building blocks. Picture this, a solid object around you, say, a football. It has 3 dimensions. Now imagine its surface, that's 2 dimensions. Trace a line across it, 1 dimension. Finally, mark a dot, 0 dimensions. So, a solid has length, breadth, and height. A surface has length and breadth only. A line has length alone, with ends at points. And a point has no part at all. Euclid listed 23 definitions in Book 1 of his Elements. For example, a point is that which has no part. Or, a straight line is one which lies evenly with the points on itself. But here's the tricky part. Words like length or breadth weren't defined further. Why? Because if you keep defining everything, you'll end up in an endless loop. So mathematicians agreed to leave some terms, like point, line, and plane, undefined. We just accept them with intuitive understanding. Welcome back. In this scene, we are diving into one of the most fundamental ideas in geometry, Euclid's assumptions. These assumptions are like the ground rules for all the geometry that follows. They're simple, but they set up everything we need to understand the shapes and spaces around us. Let's start with Euclid's axioms. These are universal truths, things that are so obvious that we don't even need to prove them. The first axiom, things equal to the same thing are equal. Sounds simple, right? Imagine you have 2 identical pieces of cake and I have 2 identical pieces. We both have the same amount of cake, that's equality. The second axiom, if equals are added to equals, wholes are equal. So, if you and I both have 2 apples and we each get 1 more apple, we now both have 3 apples. Adding equals to equals gives us equal totals. The third one, the whole is greater than the part. Pretty easy to grasp. A whole pizza is definitely bigger than just a slice of it. Now, let's move on to Euclid's postulates, which are a bit more specific to geometry. These are the rules that govern how shapes and lines interact in the world of geometry. Postulate 1. A line can be drawn joining 2 points. This is as basic as it gets. Just take 2 points, and you can always draw a straight line between them. Postulate 2. A terminated line can be extended indefinitely. Think of a line that starts at a point and keeps going without any end, like a never-ending road. Postulate 3. A circle can be drawn with any center and radius. With just a compass, you can create a perfect circle anywhere. Postulate 4. All right angles are equal. This means every right angle, whether it's in a triangle, square, or a corner, is always 90 degrees no matter where it appears. And finally, postulate 5. If a transversal makes interior angles less than 180 degrees, then the lines meet. This one's a little more complicated, but it's crucial for understanding parallel lines and angles. But don't worry, we'll come back to this one in more detail soon. Quick insight: while most of these postulates seem simple and intuitive, postulate 5 is a bit more complex. But once you understand the basics, everything else starts to fall into place. And that's the foundation of Euclid's assumptions, simple but powerful. In our next scene, we'll explore how these assumptions connect to the real world and how they help us understand the geometry of everything around us. Have you ever wondered how you can construct an equilateral triangle using just a line segment? Today, we will learn how to do this using circles and a postulate in a simple and elegant way. We start with a given line segment AB. Our goal is to construct an equilateral triangle ABC, where all the sides are equal. At first, this might seem tricky, but we can achieve this using circles and some logical reasoning. First, draw a circle with center A and radius equal to the length of AB. Next, draw another circle with center B and radius equal to BA. The two circles will intersect at a point. This intersection point is the key to constructing the triangle. Let the circles intersect at point C. Now, join points A and C and points B and C, creating the sides A, C and BC of the triangle. Now, here's why this method works. Since the radii of both circles are equal, we know that AB is equal to AC and AB is equal to BC. According to the axiom that states things equal to the same thing are equal to each other, we can conclude that AC is equal to BC. This means that the two sides AC and BC are equal. As a result, triangle ABC is equilateral because all three sides AB, AC and BC are equal in length. This simple but powerful application of circles gives us the desired equilateral triangle. Isn't it amazing how geometry and logic can work together to create such beautiful shapes? Now, here's why this method works. Since the radii of both circles are equal, we know that AB is equal to AC and AB is equal to BC. According to the axiom that states things equal to the same thing are equal to each other, we can conclude that AC is equal to BC. This means that the two sides AC and BC are equal. As a result, triangle ABC is equilateral because all three sides AB, AC and BC are equal in length. This simple but powerful application of circles gives us the desired equilateral triangle. Isn't it amazing how geometry and logic can work together to create such beautiful shapes? In the next video, we will continue exploring more geometric concepts and see how they help us solve other exciting problems. Stay tuned. So, let's wrap it all up. Geometry began with practical needs like measuring land and building temples or pyramids. India contributed through altar designs, Greece through deductive reasoning, and Euclid tied it all into a systematic masterpiece, the Elements. We learned that some terms like point, line, and plane remain undefined, but they are our foundation. From there, Euclid built his world using axioms and postulates. And finally, we saw how simple constructions, like an equilateral triangle, come directly from these principles. Remember, Euclid's geometry is not just about shapes, it's about the power of logic, the beauty of reasoning, and the elegance of starting from the simplest truths to build a whole world of mathematics. And that's the foundation of Euclid's geometry. In the next video, we'll explore how his postulates lead to powerful theorems and logical proofs that still guide us today.